Guys, welcome to today's webinar on performance metrics for GPU programming. So a lot of you guys are interested in faster programs, writing your applications to be more performant, and how do we measure application performance? What is it that goes into measuring how many milliseconds a process might take? So that's kind of what we're gonna talk about today for this webinar on performance metrics. Let's get started. So the first concept we're going to talk about is execution time. All right, so we measure the time it takes for your program to run both in serial on the CPU and in parallel on the GPU. This is the most basic and important metric. So the time for a program to run start to finish, right? Typically in milliseconds, both in serial on the CPU and in parallel on GPU. And we use precise timing functions or profiling tools to get accurate measurements. So execution time is sort of the most basic measurement there is. Typically in milliseconds, a process can run from start to finish on the CPU and GPU, and we that's how we measure that. Pretty straightforward. Then there's the speed up measurement. What is speed up? Maybe you've heard of this term before, maybe not. It's okay. So the speed up is the ratio of the serial execution time to the parallel execution time. All right, so if you remember, the serial execution happens in CPU, parallel in GPU. So the speed up ratio is serial time over parallel time. It's a ratio. All right, it indicates how much faster your program runs with parallelization, right? Because ideally the parallel execution time is going to be faster. Right, so the ratio shows you sort of how much faster. Ideally, speed up should increase linearly with the number of processing units, GPUs, but in practice, it's often less due to overhead. So that's why we love GPU programming for its speed, and then speed up measurement, the ratio, indicates how much faster the program runs. Then there's efficiency, right? What is efficiency talking about? Measures how well the processing units are utilized. This is speed up divided by the number of processing units, right? Whether it's 4, 8, 16, 32, however many you have, you divide the speed up by the processing unit to get the efficiency of your software. It represents the fraction of the ideal speed up achieved. A higher efficiency indicates better utilization of the GPU resources. All right, guys. So those are some key terms I wanted to share with you guys today. And last but not least, scalability. All right, scalability refers to how well your program's performance scales with an increasing number of processing units or problem size. So there's strong and weak scaling, and we'll go over each of those now. So strong scaling measures how the execution time decreases as you increase the number of processing units while keeping the problem size fixed, whereas weak scaling measures how the execution time changes as you increase both the number of processing units and the problem size proportionally. All right, so there's weak and strong scaling. And it took me a minute to figure out the difference here, but it's referring to how well your program's performance scales with an increasing number of processing units, or the problem size might increase. And you might have more processing units, a better GPU, for example, or more inputs into your program. So strong and weak scaling. All right, so strong scaling. So in strong scaling, the problem size is fixed, whereas in weak scaling, the problem size is not fixed. All right, 3 more terms we got to go over: GPU utilization, memory throughput, and kernel performance. All right, so GPU utilization, we monitor the utilization of the GPU during program execution, and this can help identify bottlenecks or inefficiencies. Tools like NVIDIA Visual Profiler or NVIDIA Nsight Systems can provide detailed information about GPU utilization, memory access patterns, and kernel execution. All right, so look into NVIDIA Visual Profiler if you're interested in that. There's memory throughput, which is a measure of the rate at which data is transferred between the host and the device, as well as within the GPU's memory hierarchy, the memory throughput. Memory transfer can be a significant bottleneck in GPU programs, so optimizing memory access patterns is crucial. And last but not least, kernel performance. We want to analyze the performance of individual kernel functions, which are the core of your GPU program. So metrics like kernel execution time, instruction throughput, and warp occupancy can provide insights into kernel efficiency. So these are some more advanced concepts. So once you've mastered the first four, you might want to look into learning about these three. And then last but not least, we're going to end today's webinar by discussing Amdahl's law. Have you guys heard of Amdahl's law? So it states that the maximum speed up of a program is limited by the portion of the code that cannot be parallelized. It's important to consider Amdahl's law when evaluating the potential benefits of parallelization. So it all goes back to Amdahl's law, right? I guess there's it's limited, right? It states that the maximum speed up is limited by the portion of the code that can't be parallelized. It's a tricky word there. So always remember Amdahl's law when analyzing performance bottlenecks. But hopefully that was helpful, guys, in thinking about how we measure speed and efficiency when GPU programming. If you have any questions, drop them in the comments. I'll try my best to answer them for you. And yeah, guys, see you next time for a future webinar where I'll delve deeper into some of these topics related to GPU programming, both for NVIDIA as well as AMD GPUs. As always, thanks for subscribing. I'll see you next time.